Section 4.5 looks at several properties and rules of logarithms that we should be really comfortable with as we work through these. So first one, let's take a look at some numeric properties. In that we did a few of these in class already, but it's good to summarize them. So the first one is log base b of 1 equals what? What could that equal? Well, what we saw in class is that it's 0, because if we convert it to exponential form, b to the 0 equals 1. As long as the base isn't 0, but we already know that the base of logarithms and exponents are just greater than 0. So b to the 0 equals 1, so therefore log base b of 1 does equal 0. Now, second one, log base b of b, what could that equal? Well, again, we saw that it's 1 because b to the 1 is equal to b. So this b down here is really the base b. So base b raised to the 1 equals b, and the second b is the one that was inside of that logarithm on it there. So those are just some two basic numeric properties. The next two get a little bit trickier. They're called the inverse properties, in that log base b of b to the n is equal to n, because as you can see, if we convert it, we have base b here to the n, there's base b to the n, equals what's inside, which is b to the n. So the inverse property just simply says if you have log base b of exponential base b, those cancel out and you're just left with n, the exponent. Similar to the number 4, where you've got exponential base b raised to the log base b, again, they're inverse functions, so it equals n. Our exponential base b and the logarithm base b, they're inverse functions, so they do cancel with each other on it there. So there. And they'll cancel. So to see how these properties can work, the inverse properties on example 1, if we want to simplify these, first one is log base 7 of 7 to the 5. Well, that should cancel to just be 5 on it there. And again, you can see why, because if you converted it into exponential form, you would have base 7 raised to the 5th would equal 7 to the 5th on it there. So kind of easy to see how that would work. Part B, we've got the natural log of e. Again, they're inverse functions, natural log of e to the negative 2.45. So that should cancel out and just leave us with negative 0.245. And the same thing with part C is 10 raised to the log. That's the common log, and remember the common log is base 10. We just don't see that subscript of 10 there. But 10 to the log base 10, again, will cancel out, and that will just leave us with pi on it there. The next three properties are the algebraic properties. And the first one is the product rule, which says if you've got the log of a product, so the log of x times y, that product can be split up into a sum. We've got log base b of x plus log base b of y. So a product turns into a sum. An example would be if you have, let's say, log base 10 of 35, that's really log base 10 of 7 plus log base of 5. Kind of squeeze that in here, there. So since 35 is 7 times 5, we can split this log of 35 up into log of 7 plus log of 5. Now, similarly, if we have quotient, so we're dividing log base b of x divided by y, that is log base b of x minus log base b of y. So the product turns into an addition, but a division turns into a subtraction. So another example of this would be if we've got, let's say, the natural log of 5/3, that would be the natural log of 5 minus the natural log of 3. So a division turns into a subtraction. Log of the numerator minus log of the denominator. Our last algebraic property is the power rule, in that if we have log base b of x raised to some kind of a power, so x to the nth, we can rewrite that as n times log base b of x. So it really just looks like that power n came down in front of the log there, and it just left us with the n times log base b of x. An example of this would look like, suppose we have log base b of x to the 4th. This is written as 4 times log base b of x. So it just looks like the 4 comes down in front. And we'll kind of prove that in a second here. But first, let's prove the product rule. So if we want to prove the product rule, let's say, let's look at the proof of log base b of x times y equals log of x plus log base b of y. Oops, I forgot my b on my first expression, right? Log base b there. Probably missed that a few times here. So if we want to prove this, let's start out with a couple of expressions. So here's our little proof. Let's let x equal b to the s, and let's let y equal b to the t. So now both of these exponential expressions can be converted into logarithmic. So we've got log base b of x should equal s, and log base b of y should equal t. So that we know from class with our properties of logs and exponents. From here, let's do a little calculations. Let's find what x times y is. So x times y should be b to the s times b to the t. That was our definition up here of what x was and what y was up there. Now, we know the properties of exponents. When you have common bases multiplying each other, we can add the exponents. So x times y is b to the s plus t. Now, let's convert this expression back into log form. So what would that look like in log form? This will be, well, this is our exponential rule, adding the s plus t. So the log form is log base b of x times y should equal s plus t. But wait a second, we already know what s plus t is. That was given right up here. S is log base b of s, and t is log base b of y. So if we replace those, we get log base b of x times y equals log base b of x plus log base b of y, and there's the proof of that rule. Now, it's similar to if we wanted to prove the log base b of x divided by y. The only change would be is if we take this x times y equals b to the s times b to the t and write it as a division. So x divided by y would be b to the s divided by b to the t. That gives us x over y here equals b to the s minus y, and the steps would be the same. Converted into log form, we would just have a subtraction here instead of an addition, and that would mean we have a subtraction here instead of an addition. But the proof is pretty similar. Lastly, to prove the power rule, how to prove log base b of x to the n equals n log base b of x. This is not really a proof, so that's why I put quotes around it. It demonstrates how it works. So we can kind of demonstrate it through an example. In that, suppose we take log base 2 of x to the fifth. Well, what is x to the fifth? That's really just x times x times x times x. So this is the same thing as log base 2 of x times x times x times x times x. Get 5 of them in there. But now if we go back to the product rule, what the product rule said was anytime you have a multiplication here, you can turn that into an addition. So what does that give us? Right. Use the product rule. We'll get the log base 2 of x to the fifth is really log base 2 of x plus log base 2 of x plus another log base 2 of x plus another log base 2 of x, and finally our fifth one, log base 2 of x. But what we've got on the right-hand side now is 5 of these log base 2 of x's. So if we add them all up, we get log base 2 of x to the fifth is really just 5 times log base 2 of x's. So it really does look like the 5 exponent here simply does come down in front of the log, but it's really just a result of that product rule. So we want to use all of these product rules, quotient rule, and the power rule to simplify expressions. So if we take a look at example 2, it says fully expand the expression log base 4 of 3x squared divided by 5y. So On an expression like this, to fully expand it, let's first start with the quotient rule, which means let's split up this big division into a subtraction. So our first step is log base 4 of the fraction 3x squared divided by 5y is log base 4 of the numerator minus log base 4 of the denominator. So that's our first step. We split up that quotient into a subtraction. Now we can use the product rule to separate out the 3 times x squared and the 5 times y. So our next step is the product rule. So we'll have log base 4 of 3x squared over 5y. Again, the left-hand side should equal log base 4 of 3 plus log base 4 of x squared minus, now in parentheses we want to subtract everything, log base 4 of 5 plus log base 4 of y. So make sure you get this whole second part subtracted. So this subtraction here has to make sure everything is subtracted, hence the big square brackets. Finally, from here, we can use two things. Our power rule to bring down this power of 2 in front of the log. And we can also then get rid of the red parentheses to simplify it a little bit better. So next step, we'll bring down the power of 2, and we'll remove the parentheses on here. So what this is going to look like is log base 4 of 3x squared divided by 5y is log base 4 of 3, 2 times log base 4 of x, and then we'll have minus log base 4 of 5 minus log base 4 of y. There's our fully expanded expression. So inside of our logs, we just have either a single number or a single variable. No two variables or no powers in there on it. The other thing to notice is that any term that is positive, so this is like this positive log base 4 of 3 and this positive log, or 2 times log base 4 of x, those two terms came from our numerator, the 3x squared. The last two terms, they are both subtracted, and notice that the 5 and the y came out of the denominator. So for any positive term, that comes out of the numerator, and anything out of the denominator is going to have to be a subtraction, these two subtraction terms. Using that idea, we can simplify almost in one step expressions there. So example 3, fully expand this expression. So first thing I probably want to do is think of another way to write the square root of 6x, and remember that the square root is just really 1/2 power. So let's rewrite it using the square root of 6x as just 6 to the half times x to the half. So what that will look like is, on the left-hand side, log of root 6x over 7y cubed should be log base b to the half x to the half divided by 7y cubed. Now from here, we can almost do this in one step, and probably can. So remember, anything in the numerator is going to be a positive term, and anything out of the denominator is going to be a negative or a subtracting term there. So those are the two things to keep in mind. So we have log base root 6x over 7y is 1/2, bring the power down, log of b, 1/2 log of x, minus log of 7, and minus 3 log of y. So in one step, we know that these powers have to come down when we rewrite the expression, and also any term that is in the denominator, the 7 and the y, are going to be those subtracting terms there. So in one step, we can pretty much rewrite it as fully expanded form. Now, going the other way, in example 4, suppose we want to write all of these back. This time, to condense an expression, I usually take a couple of steps. First step is to take up all of the powers for the power rule, and then combine them together. Anything that's being subtracted is in the denominator. Anything that's positive is in the numerator. So, first, bring up the exponents back up inside there. Bring up the power. So, we have natural log of x squared minus natural log of 2 cubed plus natural log of y to the half minus log of z to the fourth. And remember that y to the 1/2 here is really a square root of y. And also this 2 cubed here, we can rewrite that as 8. So from here, now let's combine as a single log. So remember, plus is in the numerator, minus is in the denominator. So we should have one big, huge natural log expression here. So it'll be the natural log of x squared on top. The natural log of 8 is on the bottom, so that's 8 on the bottom. The y to the 1/2 is positive, so square root of y on the top. And z to the fourth is a subtracted log term, so that's in the denominator, z to the fourth. So just remember that anything negative goes down into the denominator, anything positive stays up in the numerator. So, or you could do that in a couple of steps. One of the most common mistakes in doing a problem like this is I've seen a lot of students want to rewrite what's inside the parentheses as like a natural log of x squared times a natural log of root y divided by the natural log of 8 divided by the natural log of z to the fourth. But remember, when you're converting from an expanded form here down to a single form, it's just a single natural log, and then everything else is inside these parentheses. So don't get caught up in the trap of trying to put all of those terms inside being also logs on there. So just to kind of pay attention that we're converting from several log expressions down to just a single log. One place where combining logs together could be handy is as example 5, a problem like this. We'll see where we get expressions like this when we start solving equations. But suppose we needed to evaluate this expression here. The 3ln2 plus 4ln3 divided by 2ln3 minus 5ln2. A lot going on there. And if we do it on our calculator, it gets pretty tricky because you've got a lot of parentheses that you're going to have to deal with there. So parentheses around the entire numerator, parentheses around the entire denominator. But each one of those log expressions also have to close the parentheses on. But if I do it on the calculator, I get something that's close to negative 5.1035. Now, a lot simpler way to do it would be combine everything in the numerator together and combine everything in the denominator together. So I want to use the power rule to bring up the 3, bring up the 4. Then I know an addition comes from a multiplication, and similar to the denominator. So we can rewrite it first as ln of 2 cubed plus ln of 3 to the fourth divided by ln 3 squared minus ln 2 to the fifth. But again, this is really on the top, just the natural log of 8 and the natural log of 81. But I know they're going to be multiplied together because of the plus sign. So we've got natural log of 8 times 81 divided by the natural log of 9 divided by 32. If we do on our calculator 8 times 81, let's see, I think what we get is natural log of 648 divided by natural log of 9/32. This time when I do it on the calculator, it's just two simple logs. One, the natural log of 648 divided by the natural log of 9/32. Really no worries about parentheses or anything. And again, we get the same exact number, negative 5.0135, which is a heck of a lot easier. The next couple of properties are, one's the change of base property, which is useful if you don't have a button on your calculator that can calculate things like log base 3 of 5. Since your calculator only has log base 10 and log base e, it's nice to be able to change the base so that you can actually calculate that expression on your calculator. The number 9, the converting from base b to natural base e, let's skip that until we get into class and we'll talk about that a little bit more. But let's take a look at the change of base formula. So first, to prove what this change of base formula is, in that it says we've got log base b of x can be written as log base c of x, where c can be anything. So normally c is going to be either base e or base 10. Those are the two logs you have on your calculator. But it looks like it would be log base whatever, c of x the number, divided by log base c of b. So let's take a look at that proof. What does that look like? So suppose I do have log base b of x is equal to something. I don't know what it is, but let's just say it's equal to some a. So log base b of x, I don't know what it is. It's equals a. But let's turn this into exponential form. So b to the a is equal to x. Now, just like any other equation, what you do to one side, you do to the other. If I add 5 to the left, I have to add 5 to the right. Well, same thing with logs. If I take the log of the left, I would need to take the log of the right. So let's take the log base c of each side. What that'll look like is log base c of b to the a equals log base c of x. So what I did to one side, I did to the other. But on the left-hand side now, I can bring down that a down in front using our power rule. So let's bring down a. We get a log base c of b equals log base c of x. I'm trying to find out what a is, so let's divide and isolate a. So solve for a, and we'll get a is, on the right, log base c of x divided by log base c of b. But wait a second, again, what is a? A is what we started out with up here. So a is just log base b of x. So substituting that back in, we have, as a, we have log base b of x is equal to log base c of x over log base c of b. And there's our proof for that power, or for the change of base formula. To see how we can use that, let's take a look at example 6, which says, evaluate log base 5 of 400. So again, I don't have that button on my calculator. It equals something, let's say, equals x. What that really means is we're looking for some number x, where 5 to the x is equal 400, but it's really just evaluating what log base 5 of 400 is. So we can convert log base 5 of 400 using our change of base. Could be the log of 400 divided by the log of 5, which is about 3.7227. Now, I just chose the log base 10, the common log, kind of just arbitrary. We could have chosen the natural log, and it would have been the natural log of 400 divided by the natural log of 5, and that gives us exactly the same value, 3.7227. So converting from base b to anything, it could be any base, but either 10 or e is going to be preferred there. Now, we can use that same idea, again, solving equations. So example 7, if we wanted to solve that equation, what do we need to do first here? Probably divide by the 3,000 there, because we want to isolate the exponential part, 1.05 to the t. So 5,000 divided by 3,000 is 1.05 t. From here, we can convert into log form. So convert. We've got log of 1.05 of 5/3. Now, what I did here is I reduced our 5,000 over 3,000, got rid of the zeros and just called it 5/3. So now I've got log base 1.05. 1.05 was our base on our exponential here, of 5/3 equals t. I can't do that on my calculator, but I can convert that left-hand side using our base conversion. So we've got log of 5/3 divided by log of 1.05 equals t. And on our calculator, we can get t is about 10.4698. So a good use of that change of base formula is once we convert our exponential equation to logarithmic, we can solve for t, we can use the change of base formula to evaluate it on our calculator, and we're done with that. Our last example is kind of a tricky little problem in that if log base b of 2 is 0.7565 and log base b of 3 is 1.1990, we want to approximate what log base b of 72 is. Now, the problem is we don't know what the base is, otherwise we could just evaluate it using the change of base formula, but we can actually do this one without finding the base, in that 72 is kind of a special number. So think about what 72 is. What we really have is log base 72 is log of 9 times 8. 9 times 8 is 72. But we can also rewrite 9 and 8. That's just log of 3 squared times 2 cubed. From here, we can use our properties, the product property and the power property to rewrite the right-hand side as log base 3 squared plus log base 2 cubed. Oops, forgot my b's on here. From here, let's bring down the powers. So we'll have 2 times log base b of 3 plus 3 times log base b of 2. But these are the things that we were given. We were given what log base b of 2 is and what log base b of 3 is in the original problem. So we can do those substitutions. These are the things that actually were given for us. So we've got 2 times 1.1990, that was the log base b of 3, plus 3 times 0.07565, and we get an answer of 4.6675. And we can actually check that by actually finding the base, which I think was 2.5. So log base 2.5 of 72 is 4.6674. So pretty darn close to what we actually got. So a little bit of rounding, but again, we only had 4 decimal places up here on our original numbers, so a little bit of rounding error is expected, but still pretty close to what we actually got, assuming that I started out with that base of 2.5.